All right, what's going on? Back again with more P5JS. Now, today we're going to build this really fun hero background. It's animated particles, and it's going to be interactive with the mouse. So you can see as I'm dragging the mouse along here that the particles are being attracted to the mouse position. And I'll show you all the different parameters you can do to play with this and customize it yourself. And it's also a great introduction to object-oriented programming. So we should get started, but first I want to mention my inspiration, which was this Particles.js library. Really cool. It has a bunch of other, in here they're using a repulse interaction, and you can like select different interactivity sort of options. But anyways, just thought I'd try to rebuild this myself in P5.
Hey there, WebBay.
All right, so here's a quick rundown of how we're going to be tackling this problem. First, we're going to draw a single particle at a random position and move it. Then we'll detect edges and make sure that our particles don't fly off the screen. Next, we will put multiple particles on the screen, so we'll do some looping here. Then we'll work on adding the mouse interaction, and then we'll add those connecting lines to make it look kind of networky. Anyway, so let's go ahead and get started now. I like to start with setting up the canvas, so we'll change this to not window canvas. We'll change it to the window width, and we'll set the height to window height. So that's great there, and then the background's just going to draw at 40, which is kind of this grayish black. Okay, now let's go ahead and define our particle class, and I'm just going to use the class keyword for that, and then capital P particle. And now this is looking a lot like a function, open close parentheses, but I don't want those here. I just want the curly brackets. And within particle, we'll define our constructor. Now, a constructor is what every class takes that tells the class essentially how to build itself. So this is how to be a particle is what we're saying. And within the constructor, we can set our properties. And the main property we're going to want to track for a particle is its position, so an X and Y value. And P5JS comes with this create vector function, which will create this for us. It's a vector object, essentially. You can look in the documentation if you're curious. This has a bunch of methods on it that we'll use to kind of add and subtract vectors from each other. So we want to set the initial X and Y, and we'll just get a random value from 0 to the window width for that, and another random value for the height. This is going to get window height from its random value. And that's good for the particle for now. So we've told it how to make itself. Let's go ahead and actually just make one and see what we get. So we'll say let P, and I'm just going to put semicolon there, and we'll set P equal to a new instance of the particle class right here in our setup function. And then we'll just console log it and inspect what we get. So save. Patricle is not a particle. So let's correct our spelling there. Patricle is still not a particle. Did I misspell it somewhere else? Yep. Particle. Okay, great. So we've console logged our particle, and we can see its position is a vector. And the vector has all sorts of methods here, like set, copy, add, subtract, multiply. And then we can see that our particle here also has an X and a Y value that are stored right here. So we're not actually seeing anything on the screen because we haven't drawn it yet. So let's give our particle a function called draw particle here. And notice we don't need the function keyword here when we're defining it within a class. So that's not needed. And I'm not calling it draw because we have our draw function up here. I just want to differentiate this from that draw function. So we have draw particle here, and all we need to do is create an ellipse. And ellipse needs the X value, the Y value, and a size. So we'll say this dot position, and we saw we have access to the X value, and this dot position dot Y. And we'll set a size to something like 5. Now within draw, we need to call p.drawParticle, and we should be able to see something on screen now, assuming that our colors are good to go. And yep, right down here, not sure if you can see it, but there's a little white particle there. And in draw particle, we'll also set no stroke, and we can set our fill to white, which it already is, but I'm just going to do it manually here too. And now we get a particle, and it showed up here, and it has no stroke on it. Okay, so we drew a single particle at a random position. Now we need to move it. So let's go ahead and give our particle a velocity. So within our constructor, we'll say this dot velocity, and we'll also set this equal to a new vector. So we'll use create vector, but we don't want to use random window width and window height here. We want to use random between say -2 and 2. So something much lower in magnitude for both the X and Y. And what we're going to need to do is update our position based on the particle's velocity. So let's, within our class, create a function called update. And so we've got open close parentheses, open close curly brackets. And what we'll say here is this dot position. So we're updating that position property now, plus equals Actually, we don't need plus equals. Again, these are vectors, so we can call this that dot add method that we saw, and we'll say this dot velocity. So that should be good to go there. We've got our update function. We actually need to call it somewhere. So let's call it right up here in draw. We'll say p.update. And again, the draw function is getting called multiple times, I think 60 frames a second by default. And so there you saw our particle get shot across the screen. Now it's going off of the screen, so that's not ideal. And we only have one right now. So let's, I have detect edges and reverse direction and put multiple particles on screen. Let's go ahead and detect edges and reverse direction to start. I was thinking about flopping that, but we'll keep it as we have it here. So let's define a function, detect edges, open close parentheses, open close brackets. Now what we're going to want to check is if the particle is ever outside of the screen bounds. So the way we can do that is get our this.position, and we'll say if this.position.x is less than 0, so it's all the way left of our canvas, and then or by this double pipe operator here, this dot position dot x is greater than window width, then we know the particle is trying to go off screen and we want to reverse our velocity, but we only want to reverse the x component of our velocity. Remember, velocity is stored as a vector up here. So what we can do easily for that is say this dot velocity dot mult, there was a multiply function, and so it's going to multiply by -1. Oh, we don't need a multiplication sign there. We'll just say -1, just like that. And we're going to say, actually, this dot velocity dot x. And I don't know if x itself has a multiply function on it, so we're actually going to need to use the times operator. We'll say times equals -1. So we're getting the x value for velocity and multiplying by itself, but also at -1, so that if it's all the way on the left edge of the screen, then it's going to just reverse and go the other way. And we can do the same thing for the y value. So let's copy this whole if block here, and we'll change x to y, we'll change x to y, we'll change window width to window height, and we'll change the x component to the y component. Now we need to actually call this function. So within update, we're adding our position, and let's go ahead and update our velocity here. So we'll say this dot detect edges, open close parentheses, and that should call our function. And since update is being called here, we should be good to go. So let's see if our little particle reverses. Yep, it bounces right off the wall there. Coming all the way over to the left side. Let's watch it bounce. Yes, it bounced. And we'll check the bottom too, and that will be all 4 corners or all 4 walls. Great. So we only have one particle on the screen. That's not very exciting. So let's work on making this more exciting with more particles. I'm going to go ahead and define a constant up here. Const num particles equals, let's set it to 20 just to not be too ridiculous to start off. And then also, rather than creating a variable for our particle, let's create a variable called particles, and we'll set it equal to an empty array. And what we're going to do is we're going to push all the new particles into this array, and we're going to use that array to track every particle that's on our canvas. So in setup, we created one new particle here, but what we should do is we should say for let I equal to 0, I less than num particles, and I plus plus. So we're incrementing the value of I every time. We are going to call particles.push. This is how we put something into an array. And we'll just say new particle, just like that. We don't need this console log anymore, but down in draw, remember we had that variable and we were just doing it for one. Now we need to do this for each particle in our array. So we can loop through our particles array, particles.forEach, open close parentheses. Now for each takes a callback function to run on each particle in the array. So we'll pass that within our function declaration there. And I'm using fat arrow syntax here. It's very similar to this syntax, but different. This came up after ES6 was introduced with JavaScript. Anyway, so we can define our function code right in here. So I'll just cut that and paste it in there. But we need to rename P to particle. And save. Let's go ahead and tidy our code. So we got our num particles, we got our particles array, we created all the particles here, and then we're looping through everything. I'm just making sure that I didn't miss anything. See, this is the power of object-oriented programming, which you could do this in functional style as well, but this may be an easier way for you to think about it. We'll go ahead and stop and replay, and now we have our 20 particles on the screen. They're all bouncing off walls, and this is working out just great. So let's introduce a little bit more fun by adding our mouse interaction. This is probably the most complex we're going to get. Anytime we're working with a mouse interaction, what I want to do is kind of have the particles get attracted to it if they're within sort of a range of influence. And to do that, I'm going to use an acceleration, because I think acceleration makes sense to kind of show like a natural motion. If we just change the velocity all of a sudden, it would look really unnatural. So let's go ahead and define a new property, this.acceleration. And we're just going to say create vector, and we're going to not give it any parameters right now. So it's just a blank vector. And what we need to do is within our update function, we will update the velocity based on this acceleration value. So we know that we can get the value of our mouse. So we'll say mouse equals create vector. And we're going to pass it mouse X and mouse Y for parameters. So we're just making another vector here. And now what we need to do is we need to kind of calculate both the distance and the direction between each individual particle, or in this case, just the one individual particle because we're within the class, right? And the mouse position. So we can use a vector subtraction for that. So let's go ahead and say let direction equal, I'm going to say mouse dot subtract this dot position. So this code right here just gets the vector that points from the particle to the mouse position. And we can also get the distance equal direction dot magnitude. So there's this dot mag function that exists on vectors that we can get like that. And now we want to check if our distance is less than some sort of value. I'll just pick an arbitrary value here. Let's say 100 pixels. Then within here is where we want to modify our velocity based on our acceleration. Now let's start out with something like the distance is going to be different for everything, right? So let's go ahead and normalize that, and we'll do that by saying direction, which again is a vector. This vector subtraction returns another vector, and we can call the normalize function normalize like that. And what this is going to do is normalize the x and the y values so that they're, if you do some Pythagorean theorem math, the unit vector or the hypotenuse is going to be equal to the value of 1. And then we'll say direction dot multiply, and here's like a multiple where we could affect how fast we want the acceleration to happen. So we'll just multiply it by half for this case. And now let's go ahead and define our acceleration based on this value of direction. So we'll just say this dot acceleration equal to direction. So we know that our acceleration is going to be essentially a magnitude of 0.5 in the direction of our mouse coordinate. Okay, now all that's left to do is take our velocity, and call the dot add method, and we'll add our acceleration. And this is going to happen each draw call. So each time this is called up here, we're going to add the acceleration to our velocity. So over time, the acceleration is going to remain pretty much the same, but the velocity is going to speed up based on that. So we can go ahead, and now this is right in our update function, which we're already calling up here. So we should just be able to stop and run this and see what we get. So I'm not seeing anything happen. Okay, so I just misspelled acceleration here, so I need to add the A, and if I save and restart, now we can see we're getting our particles to be attracted to our mouse position, and it's getting pretty fun, but it's also getting a little bit intense. So something we can do we can just limit our velocity. Right now our velocity really has no limit on it, so let's limit it to something like 4, and we save and play again. Oh, and we got an error. This dot velocity is not a function, so let's say dot limit like that. Save and now play. And we're getting the exact same effect, but things are a little bit slower, and we can come around and collect these particles, which is a lot of fun. But if we get too far, that distance greater than 100, then they will be free again. Something that might be fun as well is to have the particles start interacting with each other somehow, but that's a little bit beyond the scope of this tutorial. Anyways, we completed our top 4 things here. Now all we need to do is add the connecting lines. So let's go ahead and start working on that. But first, I want to actually clean up our update function. Let's go ahead and define a function called, actually, we will do it below the update function. Doesn't really matter where. But let's go ahead and call this detect mouse interaction. And we're just going to take all of this code right here and pull it out of our update function and drop it in here. And then, of course, we need to call our detect mouse interaction function right here. So save and make sure that's still running. Yes, everything's still working great. Okay, saved again for no reason at all. And what do we have to do next? Now we need to draw lines. So let's come on down here and we will say draw lines. And within our draw lines, we're going to want to look at our particles array, and we're going to pass it here because we don't want to look at every particle every time. We want to look at every particle the very first time, but then as we've looked at one particle, we don't need to worry about the first particle anymore. So we can proceed to the second one and then only worry about all particles after that one. So just so that we're iterating through once. Anyways, so right in here, we have draw lines. Now, very similar to how we got the distance between our mouse, we're going to get the position between the particle under consideration and another particle. So we have this dot particle is the particle under consideration, and we have particles dot essentially particle or within our for each function that we're going to get. So let's go ahead and loop through all of these particles that are passed via this variable here. And we're going to look at each particle, and then we're going to calculate a distance for that. Now, P5JS comes with a distance function that lets us do that. So I can say let distance equal to dist, open and close parentheses for our function. And now we're going to pass the x and y value of the particle under consideration and the x and y value of the other particle. So we'll say this dot position dot x, this dot position dot y, and we'll say particle dot position dot x and particle dot position dot y. And that should get us our distance between each individual particle and all the other particles. And we want to check if the distance is less than some value. In this case, we'll say if it's less than 200. And now we're going to go ahead and draw a line if that distance is good to go. Now we did say no stroke here. So remember, before we draw, we want to set a stroke. The line doesn't really use fill, it uses stroke. So we'll just call our stroke function here and we'll pass it a value of 255 for white. And then we'll draw a line, and we want to draw it from really these values to those values. The line takes the starting x and y coordinate and the final x and y coordinate. So we've got that there. Let's go ahead and save. We can see all of our particles have started bundling up over here. So let's save them. We're not seeing our lines yet. That's because we've never actually called our draw lines function. So let's copy draw lines here. Now, where do we want to do this? We want to actually do this up here in the global draw function within our for each loop here. So what we can say is particle dot draw lines, open close brackets, and now we're going to pass particles dot, we're actually going to slice this array based on an index, and we can get the index from our for each function here. So this was what I was mentioning when we just want to look at one in respect to all the others. We don't want to loop through twice each time. So save, stop, and play, and now we can see we're getting the lines to draw between our particles, and we can still interact with the particles, and it's getting a lot of fun. And we could just start experimenting like crazy. We could set num particles to 50 and play this again and get something even crazier. You could adjust the distance, to draw a line. We set 200 right here. But I think a good thing to start would be making these kind of fade in and out the closer they get. And so an easy way we can do that is right in here, rather than setting our stroke equal to white, we can also pass it an opacity value as a second argument. And the opacity should be based on the distance. So P5 has this really cool map function. We can say let alpha equal map, open close parentheses, and map takes a value and then basically how we're going to interpolate each, like the min and max to another min and max. So I think it's easier if I just write it out. So we're going to pass it the variable of distance, and distance we care about from 0 to 200. So we know that distance is either going to be 0 between two particles or up to 200 because we're within this if function. So this 200 should match this 200. So we should probably store it as a variable, but we don't need to. Actually, let's do that. Yeah, const, let's say max distance, and we'll set that equal to 200. Copy that, put it there, just good practice. Back to our map function. So 0 to max distance, we want a maximum when a particle is on top of another particle. That's a 0 distance, and we want to draw a completely white line. So 255 is good for that, for our opacity value. And when it's at that maximum distance, then we'll pass a value of 0. So what that's saying is that when it's at 200, the opacity or the alpha value is going to be 0, so you won't see the line at all. So now in our stroke function, we can just pass that alpha value and save and replay, and now we're getting these nice faded lines rather than just the complete white lines. So I think this is looking really great, and there's a ton of stuff you could just start experimenting and playing with here. But as always, we'll drag this into Webflow, and the only things that I changed here in Webflow are on the canvas, just making sure that our canvas is responsive. I have a resize. Where did I have resize? Yeah, the global window resized. I just resized the canvas with this resize canvas function. And then within our setup function, I set the display to block. I set the position to absolute. I set the inset to 0, and I set the z index to -1 so that our animation just occurs behind everything. And that is how we get this final example right here. I think I tweaked the values a little bit as well. All right, I hope this video gave you some fun ideas for your next website hero section, and also taught you a little bit about object-oriented programming along the way. As always, if the video helps, be sure to like and subscribe, and I will see you in the next one. Bye-bye.